Okay, so in this video, we're going to start finishing up our unit over thermodynamics. At the start of this unit, we talked about the difference between the terms thermal energy and temperature. And so just to kind of recap, when you're talking about thermal energy, so everything is made of, atoms and molecules. And when you're talking about thermal energy, you're talking about the taking the kinetic energy of each of those atoms or each of those molecules and adding up those kinetic energies. And so thermal energy is the total kinetic energy of all of those atoms and molecules, whereas temperature is a measure of the average kinetic energy of each individual atom or molecule making up an object. And so we talked about the difference between thermal energy and temperature, and um, and now we're going to talk about how different types of materials or different types of substances differ in how they respond when you add or remove heat. And so one of the ways we quantify that is through what's called the concept of specific heat. Okay, so this video is going to be doing problems with specific heat calculations. Okay, so let's talk about how specific heat works. So when you heat something, it should be pretty common sense that when you, let's say you add heat to an object, the object is going to gain temperature. It's going to increase in temperature because those atoms are going to gain kinetic energy, and as they gain kinetic energy, the average kinetic energy is also going to increase. And so, you know, you heat something up, the temperature goes up. Common sense. But you should probably know that not all substances gain heat at the same rate. And so the way we quantify that is through the idea of specific heat. And so the way specific heat is defined is that the specific heat of a substance is the amount of heat. Remember, that's the amount of thermal energy needed to increase 1 kilogram of a substance by 1 degree Celsius, or you could also say 1 Kelvin. Okay, so specific heat is the amount of heat needed to increase 1 kilogram of that substance by 1 unit of temperature. Right, and so that is the definition of specific heat. But let's talk about, what exactly does that mean? And the way we're going to do that is by looking at the specific heat equation, which is written like this. Okay, and so this equation is the Q-mc delta T equation. All right, and so in this equation, we're told that Q is equal to mc delta T. Now, what does that mean? Okay, so Q, remember, is heat. So on the left side, you have heat either being gained by an object if it's positive Q, or lost by an object if it's negative Q. On the right side, you have the mass of the object in kilograms, of course, because that's masses in kilograms. Um, it's written on the screen as an uppercase C, but the symbol for specific heat is really a lowercase c. And so when you're talking about specific heat in the equation, that is represented by this term here, that's C. And then we have this, what we call delta T. Okay, so the triangle looking thing, that's the Greek letter delta, and then capital T is temperature. And the delta, anytime you have a delta, that's always a change in that quantity. Okay, so for example, when we did change in momentum, we did final momentum minus initial momentum. Anytime you ever have a change in something, that means you take the final value and subtract the initial value. And so when we write delta T like this, what that means is change in temperature. That means the final temperature minus the initial temperature. Okay, and so basically what we have here is, if we add heat, on the left side, the temperature is going to change on the right side. And the two factors that affect, like how much does the temperature change, are what is the mass and what is the specific heat. Okay. Now the mass probably common sense because obviously if you have more mass of something, then when you add heat, the temperature is not going to change as much because that energy is spread out over more atoms. But specific heat is basically dependent on the material that you're talking about. And so different materials have different specific heat values. So for example, if I have, let's say 2 cups of water, a big cup of water and a small cup of water, the big cup of water might have more mass, obviously, but as long as it's water in both cups, they have the same specific heat. Okay, because water has one specific heat value, and usually you can look these up in like tables and stuff. So when we're doing problems with specific heat, you'll see like tables with different values based off of what the material is or what the object is made of. Okay, so let's take a look at doing calculations with this specific heat equation. Okay, so make sure you have that added to your notes. Okay, and so this is the kind of table that I was telling you about before. And so this is not like every single material known to man, but this is just like a few different materials along with your specific heat values. And so, for example, aluminum has a specific heat value of about 903. Okay, now what does that mean? Like 903 what? So remember, the definition is the amount of heat it takes to change 1 kilogram of that substance by 1 degree. And so when we say aluminum has a specific heat of 903, that means it would take 903 joules of heat to heat 1 kilogram of aluminum up by 1 degree Celsius. Okay, so that's what that number means. And so, in simple terms, um, the specific heat basically tells you how easy it is to change the temperature of something. Okay, the higher the specific heat, the more thermal energy is needed to raise the temperature of the object by 1 degree. Okay, so what that means is, in other words, an object with a high specific heat is going to take more energy in order to increase its temperature. Okay, or the reverse of that, it's going to release more heat when it cools off. And so if you look at the chart, for example, lead, um, let's say I have a kilogram of lead and I want to raise the temperature by 1 degree, I only have to put 130 degrees, 130 joules of energy in. Whereas if I take like water, I have to take 4,180 joules of heat just to take the same amount of the same mass of water and raise its temperature by 1 degree. And so lead is much easier to heat compared to water because it has a much lower specific heat value. So let's take a look at some simple examples with the equation. Okay, so example one. Example one says how much heat must be added to a 50 kilogram sample of lead to increase its temperature by 100 degrees Celsius. Okay, so I'm going to identify my givens, and here I've got the mass, of course, 50 kilograms. When you're doing problems with specific heat, you're given a table, and you have to use the information in the table to answer the question. So for example, when it says that it's made of lead, I'm going to find lead on my table, and I'm going to see that lead has a specific heat value of 130. Now when I go to plug into my equation, the question is asking how much heat. Heat is Q. Okay, so I'm looking for Q. I'm given the mass is 50. The value of C I use based off of the material because it's lead. I'm doing 130, so I'm going to do 50 times 130 times the change in temperature. Now, normally delta T is the final temperature minus the initial temperature, but here they actually give me delta T because it says increase by 100 degrees Celsius. Okay, that means delta T is 100 degrees Celsius. That doesn't mean the temperature is 100 degrees. It just means that the temperature changes by 100 degrees Celsius. And so for delta T, I'm just going to plug in 100, and then I'm going to do this calculation. So in my calculator, I'm going to do 50 times 130 times 100. Okay, now what if it wasn't lead? What if it was aluminum? Well, then I would be doing like 50 times 903, because that's the specific heat for aluminum, times the 100. Okay, and so the specific heat again depends on what material you're talking about. And so this value is going to be, let's see, 650,000 joules of heat. Okay, which sounds like a lot of energy, and it is, but then again, 50 kilograms of lead is a lot of lead also. Okay, so that is example one. Pause there if you need to look at that some more. Okay, so let's do some other examples. Okay, so example two says, how much heat is released when a 0.45 kilogram piece of aluminum cools from 45 degrees Celsius to 15 degrees Celsius? Again, we're looking for heat, okay, which means Q is our unknown. And we have the equation. Remember that delta T, when you write delta T, anytime you write change in, that's always final minus initial. And so we're going to have two different temperatures in this problem. So we have the mass. Because it's aluminum, I'm going to go over to my chart and find the specific heat value for aluminum, that's 903. And then delta T, I have two temperatures. The initial temperature is going to be 45 degrees Celsius. and the final temperature is going to be 15 degrees Celsius. Now, how do I know which one is which? Because it's starting at 45 and then it's going down to 15. So when I get to do this calculation, I'm going to do the mass, which is 0.45, times the specific heat, which is 903, times delta T, which is T final minus T initial. And so I'm going to multiply by, parentheses, 15, that's the final, minus 45, which is the initial. Now, if you look at this, 15 minus 45 is going to be a negative, actually. And so we're actually going to end up with a negative value for our answer. And the reason we get a negative value, let's say it looks like that answer is negative 12,190.5 joules. So why do we have a negative Q? All right, so here we have a negative Q because heat is being released. Okay, and so basically you can think like, okay, when heat is going into something, when heat is being absorbed by an object, the temperature goes up, so that is a positive Q. When an object cools down and it releases heat, that means the temperature goes down. That's when you have a negative Q. Okay, so positive Q, heat's going in, negative Q, heat's coming out. Okay, so pause there if you need to look at that some more. All right, example 3. When 5,000 joules of heat is added to a glass bowl, the temperature of the bowl changes from 24.5 degrees Celsius to 30.2 degrees Celsius. Calculate the mass of the bowl. Okay, and it's a glass bowl. Now, I want you to pause it here and try to do example 3 on your own. Okay, so we have 5,000 joules of heat, so this is Q. We know it's a glass, so I'm looking over here and I'm using the specific heat value for glass, 664. And I have the initial temperature and I have the final temperature, so this is TF, and then this is TI. I don't have the mass, which is my unknown. So when I get to plug in, I have Q equals MC delta T. Q is 5,000. The mass is unknown. C is going to be 664 because it's made of glass. And then for delta T, I have 30.2 minus 24.5. So don't forget delta T is always the final temperature minus the initial temperature. And so I can simplify that because I can do 30.2 minus 24.5 and then multiply that by the 664. Okay, so I actually get the mass times 3784.8. All I did was I just did that subtraction and then I multiplied by the 664. So now to get mass by itself, I just need to divide both sides by the 3784.8, divide by 3784.8. And so in my calculator, to get the mass, I'm doing 5,000 divided by 3784.8, and I get 1.32 kilograms. Okay, and I only put two decimal places here just randomly. Remember, usually in the problem, it will tell you how many decimal places to put. Okay, so pause there if you need to look at that some more. Okay, so let's talk about something really quickly before we get to two object problems. So hopefully you notice that metals tend to have a very low specific heat value, meaning that they change their temperature really easily. And so one reason, for example, that or one application of where we use metals is, for example, in cooking. And so if you think like cookware, typically is made of metal like copper or aluminum sometimes. And the reason for that is because they have a low specific heat value, it's very easy to change the temperature of metals as opposed to, for example, water, which has one of the highest specific heat values. Okay, and so that's why we use metals in cooking. Whereas water has a high specific heat value, like I said, which is good because if you think like, most of the earth is made of water and the temperature of the oceans doesn't change very easily because water has a high specific heat value. And if water, let's say the temperature of the ocean changed like drastically from night to day, then we would have like crazy weather storms on Earth, and the Earth would not be livable because of all the horrific weather. Um, but luckily, water has a very high specific heat value, and so that doesn't happen. All right, so let's do just a few more examples. I want to talk about a special type of problem called a two-object problem. And so this is a device called a calorimeter. And basically, a calorimeter is used like if you ever go to like McDonald's or something and you see like the calories on the menu, the way they find the calories for that food is using what's called a calorimeter. And this is just like the simple version. But basically, the way it works is they take the food, right, and they basically like blow it up or they like burn it or something, and so it releases heat. And the idea is you have the container inside some water, and when it releases heat, the heat goes into the water, and the temperature of the water is going to go up because of that. And based off of how much the temperature of the water changes, you can find out how much energy was in that thing that you just like blew up. Okay, and so a calorimeter is that type of device. And that's I'm simplifying, but that's basically how they find like how many calories are in different food items. Is that they just like burn it or whatever and have the heat go into water. Um, and so this idea is what we call like a two-object problem, because here we basically have two objects, right? We have the water, plus we have the object that we're like uh, um, setting on fire, like inside, or not setting on fire, but like uh, exploding or whatever inside the water. And so those are two different objects. And so we have heat going out of one and into another. Okay, and so what we're going to do now is look at what happens when we do calculations with two objects. Okay, so here is the principle. If you have two objects in thermal contact, we know that heat is going to go from the hotter object to the colder object until they reach thermal equilibrium. We've talked about that before, where they have the same final temperature. That's important, by the way, the same final temperature. Because energy is conserved, all of the heat that goes into the colder object is equal to the heat that comes out of the hotter object. Okay, the heat that the hotter object loses must be equal to the heat gained by the colder object, assuming that no heat is lost to the surroundings. So the way we write that mathematically is we say Qin equals minus Q out. Okay, the heat going in is equal to the heat coming out of the other object. So this is the equation you always use for two object problems. Okay, don't forget at the same time when we write this, Q is also equal to MC delta T. Now, how do you know like which one is which? Like, how do you know which is Q in and which one is Q out? Well, whichever one is like gaining heat is Q in, and whichever one is losing heat is Q out. Okay, so it's that simple. So we're just going to do a few problems with two object problems, and then we'll be done with this unit. Okay, so let's take a look at example 6. Okay, so example 6 says a 1.5 kilogram sample of an unknown metal is heated to a temperature of 220 degrees Celsius. When you're doing these problems, by the way, you're going to have two masses um, that you need to label. So I'm going to label this mass 1. Okay, so we have a 1.5 kilogram sample of an unknown metal is heated to a temperature of 220 degrees Celsius. So I'm going to label this T1 initial. It's then placed in a bucket which has water. So I'm going to call this mass 2. Because it's water and I know it's water, I would look at my table of specific heat values and I would see that the C value for water is 4200. I realize that I don't have that table on this slide. I apologize, but you would have that given to you like on a practice assignment or on a quiz or test. And the water has an initial temperature of 25 degrees Celsius. This is going to be T2I. When the system comes to thermal equilibrium, and this is really important, remember at thermal equilibrium, both objects have the same temperature. When the system comes to thermal equilibrium, it says the water has a final temperature of 35 degrees Celsius. But you need to know that if it's thermal equilibrium, they have to have the same final temperature. So look at the first question. What is the final temperature of the unknown metal after it comes to equilibrium with the water? Well, the final temperature of the water is 35 degrees. And so that means the final temperature of the metal is going to be 35 degrees because it's thermal equilibrium. So the final temperature is the same. All right. So normally what I would do is I would do Qn equals minus Q out, and I would solve whatever they want me to find. But here they're just asking how much heat was gained by the water and how much was released from the piece of metal. Okay, so Qn, so the heat's going into the water, so Qn is going to be for the water. So I have the mass of the water times the specific heat of the water times delta T of the water. That's Qn. Well, the mass of the water is 3, specific heat of water is 4,200, and then the delta T for the water is going to be the final minus the initial temperature of the water. And so that's going to be 3 times 4,200 times 10. That's 126,000 joules. How much heat was released from the piece of metal as it cools? So think about that and try to answer that. So how much heat was released from the piece of metal as it cools? Well, it's the same amount of heat that just went into the water because Qin equals minus Q out. So the heat coming out of the metal as it cools is going to be negative 126,000 joules. It's the same number, but it's negative because it's being released. Okay, so again, in a two-object problem, Qin equals minus Q out. All the heat coming out of the hot object goes into the cold object. All right, so pause there if you need to look at that some more. Okay, now we're just going to do one more example. Okay, so this is example 7. All right, so very similar setup. Basically, actually, it's like the same setup now that I look at. So I'm just going to label this again. Okay, so we have the mass of the unknown metal. We have the initial temperature. So now I'm actually going to do this problem and I'm going to solve for something. Okay, so this is normally what you would be doing like on an assignment. Okay, so this is T2I, and this is T final. So if I use the equation Qn equals minus Q out, watch how I do this. So Qn, it's going into the water, so that's M2 times C2 times delta T2 equals minus Q out. That would be M1, C1, and delta T1. And I always have people always ask me like, how do you know which one is which? Let me tell you, honestly, it doesn't really matter if you get the value switch. Like if you get your Q-ins and your Q-outs like flipped, you'll still get the same answer. Okay, as long as you're consistent with everything. So don't worry too much about that. So when I go to plug in values, I have mass 2. Okay, that is 3. C2 is 4,200. Again, normally we would have a chart telling us that, but it is 4,200. T final minus T initial equals negative mass 1, which is 1.5, times C1, which is my unknown because I'm asked what is the specific heat of the unknown metal, times delta T of the metal. And so the final temperature is 35 minus the initial temperature, which is 220. Okay, and so now all I need to do is I need to simplify and solve. On the left side, I have 126,000. I just remember that from the last problem. And on the right side, I can combine 1.5 times 35 minus 220 and get positive 277.5 times C1. So if I divide both sides by 277.5, divide by 277.5, I get C1 equals, let's see, 126,000 divided by 277.5. I get 454 is my value for C. Keep in mind, C is always a positive value. Okay, you can't have negative specific heat. All right, so that is it for example 7, and I'll probably do a couple more examples when I see you in class. All right, so as always, please let me know if you have any questions, and I'll see you guys in the next video.